hello, functional programmers. We're here to learn about higher order functions. I hope everyone feels okay after the midterm. That will be graded relatively swiftly, and by swiftly I mean we're not going to do anything with it in the next like 3 days, but it will be graded eventually. Now we're at this certain point in the semester where I've sort of told you all of the really core things I believe are really important for being a functional programmer, and we're not there yet. We're not done. But this lecture, I think, maybe this lecture and the next lecture are going to be the last things that are really fundamental, I feel. The rest of the semester will be like case studies, particular niches, and techniques that are important but aren't like essential in functional programming and in software design in general. So when we conclude this lecture, and indeed when we conclude Thursday's lecture, you're going to be well equipped to pretty much tackle whatever problem you want, I claim, by using a functional language, SML, whatever. I think you could do my job after learn this in the next lecture. Higher order functions is really the last bastion of like really core important stuff. So that's worth noting. All right. Oh yeah, something I was going to show you as well, because this is contentious, is house points is close. It is close. There's an opportunity. Honestly, there's an opportunity for I Love Brandon because I said I would not feel bad about giving them 20 points if they won today. So if I Love Brandon won twice, like I would totally be fine if they tied. So I'm totally okay with that. You know, like, so just letting you know. All right. Cool. Awesome. Let's get started with lecture. All right. Higher order functions. This is easily one of my favorite topics in the whole course. Let's get into it. So remember Menti. Your old pal Menti, you can ask questions anonymously. Please ask at that link and ask real questions, please. There's only so many minutes in a day. But yes, that's the code. I don't choose the codes, or I would have chosen something more auspicious. Okay. But if I trust everyone's copied that down, so otherwise we'll get going. Okay, so we only have 3 things on our docket for today. We're going to be talking about this idea of these things called higher order functions. We're going to explore the HOF Zoo, I call it, which is really like a collection of 5 really core higher order functions that would be good for you to know. And then we'll talk a little bit about some of the theory and the math, in particular how we can use that to help our equational reasoning and how we write our proofs. Okay. Okay. So this last time is now actually kind of relevant, so I'm going to talk about it. But remember that last time we took a midterm, but last time we learned about parametric polymorphism, and we saw that we could have these polymorphic types, which were themselves like a family of types, right? We could have values that had polymorphic type that could then be used in all sorts of types, like nil. Nil could be used as an int list, as a bool list. Generically, we could use them at each use site. And then we also use it to define polymorphic data types, like the true definitions of option and list. And then we looked at a case study of polymorphic sorting, where we wrote merge sort, but now we equipped it, or rather, I went through 2 slides where merge sort was augmented with a comparison function, which then let us define every sorting function ever. Okay, and we're going to see that that idea is pretty much what we're talking about in this lecture. So I had this idea where I said we have a family of types. I said like a polymorphic type, like alpha, kind of has like a lot of types to it, right? Like alpha is in a family because you have alpha star beta that comes from it. You have, int that comes from it. It's like hereditarily, every type sort of descends from alpha. Similarly, we have like length, but like the length function actually has many instances of the length function. Like we have length, which takes in an int list, right? And returns to us an int. And then similarly, we have the length function, but this one takes in a string list and returns to us an int, right? It's a family of a bunch of things, a bunch of common models that are related by this idea of alpha, this general alpha, or this general length, and so on and so forth. And a polymorphic function was this one, right? But these ones do essentially the same thing, if you think about it. Like length, the reason why length is polymorphic is because whether or not you're counting an int list or a string list, the code for length looks exactly the same, right? So polymorphic functions seem like they have to do exactly the same thing. They're not that useful, right? Except for code reuse. That's actually not strictly true because we have this idea of higher order functions, which are not just polymorphic, but are going to allow us to change the behavior of our functions as well. Okay, so with higher order functions, we can use this to abstract away design principles themselves, common patterns in code, I claim. All right, I'm going to show you how that is. This is Annoying me. Oh, it went away. All right, never mind. Cool. All right. So recall that we had a polymorphic sorting function which looked like this. We had sort, which took in our CMP function, and it took in an L of type alphaless, and then whatever came after. All right. This one is polymorphic, but it doesn't do the same thing, right? Because depending on this comparison function I give it, it could do anything. It could sort in decreasing order. It could sort a list of strings. It could do very widely varying things. So this is an example of where higher order functions, we actually get into something more powerful than just doing the same thing but at different types. So it's because, surprise, surprise, sort is not just a polymorphic function. It's also higher order. And that combination of being both polymorphic and higher order is what's going to give us this kind of power, all right? Let's look at it specifically. So when I say higher order, I want to contrast that with this idea of first order functions. With the first order function, like most of the ones we've written this semester, they've taken in tuples, right? It's been like of type T1 star T2 usually, or maybe it has a few more things, and it returns to us like int, or it returns to us like int option. Or if we get really fancy about it, sometimes it returns to us int list, okay? We've had a little bit of an over-reliance on these int types. But the point is that these things are first order because function types never appeared. T1 and T2 never had function types. The idea behind higher order functions is that we can take in a function and return a function also. Remember, functions are values. They're treated the same as any other type, any other value, any other thing that I can hold. Okay, the same way I can hold an int in my hand and I can manipulate it, give it as an argument to some function, I can do the same thing with functions. So that is the idea here behind this idea of higher order functions. All right, I'll let you copy that down briefly. Okay, no, it's back. What even is it? Is it LaTeX? I don't think it was LaTeX. It was blue, I thought. All right, well, you know what? All these got to go. Cool. All right. Yeah, you know. Okay. So sort's a higher order function because what does it do? It takes in this function I just told you, right? By taking in a function, we've abstracted it over all the possible sorting functions we've given it. We can customize based on that. But how else can we do this? So let's see it. Here's how we could use sorted, right? Or the sort function I just talked about. We could define this function called mod12 compare, and then we could, which takes in two things and then does their int comparison mod12. And you should be able to assure yourself this is type int star int to order, okay? And then we just pass it in right here to sort on 4, 3, 1, 2. And this should give us, well, 1, 2, 3, 4. It's a non-interesting mod12 sort, but it is sorted mod12 nonetheless, okay? And that's the idea of how we'd use this. But that's just one presentation. We're going to look at a different way of doing it, okay? And in particular, I kind of hate that I had to write out mod12 compare, all right? One thing I've thought about is programmers are especially good at coming up with names for things. Okay, we have to come up with names for things on the fly for a lot of. If there was a competition for naming children, we'd probably win. But I don't really want to have to come up with this name because it clutters my workspace. Now I have to look at another thing. I have another thing I could possibly mistake. I don't want to do that. So how can we do that? Actually, I'm going to write it out here. Okay. So instead of that, what we're going to do is this. Well, actually, does anyone have an idea? What are we going to do? You probably already know. Lambda expression, I like it. Just because the haichus are in the bag doesn't mean that they're not here. All right. We're going to do a lambda expression. So instead of defining this mod12 compare, I'm going to say fn x comma y goes to int.compare x mod 12, y mod 12. Left paren, or right paren, 4, what was it, 4, 3, 1, 2? Oh, well, I don't care actually, but, so this is how I would do it. I can do it in place. One of the really great things about lambda expressions that we haven't really seen so far is I can just spin up a function on the fly. I don't have to give it a name. I don't have to bind it. I don't have to put it on its own line. If I want a one-time function I can use for something, like a sort, I can just immediately go and use it. This is a really important thing, especially when dealing with higher order functions. But this is what I do. So yes, that's exactly what I was going to write on that side. Okay. So this is the case of when we take in functions. What about when we return functions? Let's talk about this. We have this idea called currying, which is when a function returns a function. And the name is interesting because the name actually comes from this guy called Haskell Brooks Curry, who was a master in this field called combinatorial logic. And I feel like stressing this guy to you because this guy has not one, not two, but 3 programming languages named after him. There's the Haskell programming language, the Brooks programming language, or Brook maybe, and the Curry programming language. So this guy's a big name, all right? You should know that. If you pay enough attention in this class, maybe you too will have 3 programming languages named after you. But Haskell Brooks Curry, and we have this idea of currying. So how does that look? Well, let's try it this way, okay? Yes, I do remember what I was going to do. I can write this. Would anyone like to tell me what this function does? Would anyone like to hazard a guess? It adds 2 numbers. Okay, the add function adds 2 numbers. That's great to know. Another thing to know, what's its type signature? What's its type? Int star int to int. So let's write that. Well, for reasons which I will leave opaque, I'm going to present to you a different way to do this. All right, and I like to kind of give you this metaphor of suppose I think I read this in a story or something once, but suppose you build teleporters, all right, and you want to go to China, but your teleporters only go 50 meters. What do? You teleport the teleporter. You put the teleporter into the teleporter. So here's the idea, all right? I'm going to define a function which returns a function. It's going to be called cadd. And the idea is, once I've taken in one argument, which is my first integer to be summed, what I'm going to immediately do is return to you a function. I'm going to return a lambda expression taking in y, which then evaluates to x plus y. We haven't really had reason to do anything like this, but this is something that if you kind of adjust your mental model of how SML works, you should be able to be totally cool with this, okay? And that's kind of interesting now, right? Because do you first of all, do you believe this is legal syntactic SML code, right? What's the type? What's the type of this? Yeah. Yeah, int quantity on the last one. Yep, that's correct. Actually, yeah, okay, cool. I like to predict myself. I like to not actually look at what I'm going to do next and then see whether or not I got it right. So you're correct. That's int2 parens int arrow int. It actually turns out that these function type arrows are right associative, meaning that if I write this is actually the same as this. So we can actually omit that if we want. But yeah, good observation. So int. So the way we would say this is int, int, or we'd say int to int to int. And that is our curried add function, okay? And it kind of feels like these two should do pretty similar things, right? Because what's one way I could use these functions? Well, I could use the add function. What I'm going to write is I'm going to write val, underscore equals add of 2 and 2, or 2 and 3. All right, you believe this is going to be an integer. But I can also, how would I use cadd? Well, to use cadd, what I'm going to do is I'm going to first pass in this x, okay? Now what I have for you is, okay, let me actually display it to you this way. Cadd has type int to int to int, right? Where this is implicitly this. What is the type of cadd2? Int to int, right? We're just going to follow simple rules to do that. I can't give a high true to all of you, assuming you said that. So now, if this is of type int to int, I can just give it an int as a function, right? So let me do it. Except that parentheses are evil, so let's not do that. We're going to do this, because this is actually understood to be the same thing, because function application is left associative, so this is implicitly parens around here, okay? And these look pretty much the same, right? But there's a little difference in intention between how I do this. Here's a question for you. Are these functions extensionally equivalent? No, why? Yes, they do different things, even though in intention they kind of do the same thing. I'm going to hit you in the face. There we go. They can't be extensionally equivalent because extensional equivalence is only a relationship on things of the same type. Okay, so they're not extensionally equivalent, but they correspond. They kind of do the same thing. And we're going to see that it might not be obvious why we want to do this, but I'll explain that. Yeah. So anything that you put here is a pattern, and underscore is a valid pattern. When I do this, I basically mean I'm exhibiting this computer science thing, or programmer thing to you, where I don't want to come up with a name for this. Oh.
If you actually type that into SQL.
No, this is not a variable.
Okay.
Yeah, actually, my first internship ever, outside of after my freshman year, I was doing this like machine learning thing in Python, and I was like, oh my god, like I told my best friend, like, oh my god, you can do wildcards in Python. This is so cool. Turns out you're binding to a variable named underscore, which is the worst thing I've ever seen in my life. But I was so excited. But no, this is actually a wildcard pattern, so you can't reference it. Oh, I see. Right. Okay. Yeah. It shouldn't have changed the answer of that question. It wouldn't have changed the answer. Okay. It doesn't matter. But yeah. Talk to me after class about that. He's correct. There was something about that in the midterm, but it wasn't important. Okay. Back to the thing. Let's talk about curried functions. So one thing to note also is that this is kind of gross to do because I had to write out this explicit lambda function I wanted to return. It turns out there's going to be a nicer way of writing curried functions like this. Here's how we're going to write it. And then I'm going to write x, oh my god, jeez, x, y. So here's what I just did. I put a space in between all these things. Cadd space x space y space equals. All right. If this looks to you correct, like we haven't done this all semester. We've only ever put arguments. Now, granted, they've been tuples, but they've been one thing together. All right. A tuple is one thing. This is two things because they're space separated. So this will automatically result in the binding of a function cadd, which is of type int to int to int, okay? And this is just syntactic sugar. It is just syntactic sugar for exactly this, okay? So when you write this, please do write this, all right? Don't never write this. But be aware of the fact that what's really happening is we're binding cadd to a function that takes in a thing that then returns a function that takes this in, okay? And this should also make sense to you in some form because the usage, c space arg, looks the same as cadd space arg, right? And it's also worth noting that I guess my sequencing is wrong, but this is all just syntactic sugar for this. Fair enough. So these three things, what's that math notation? Oh yeah. The following are equivalent. If you want to feel fancy, just write that. All right. So all three ways of writing cadd here are going to be intentionally equivalent to the SML compiler. Yes. What happens if you have three or more? Well, let's find out. What happens if you have three or more? Fun cadd x, y, z, w, a, b, c equals x plus y plus c plus w plus a plus b plus c. Boom. A function that takes in an int and returns a function that takes in an int that returns a function that takes in an int, so on and so forth. All right. It's not the hardest thing in the world to do. It's just a parser problem. But yes, you can iterate that process as many times as you like for however many curried arguments. It's really no different in intention than taking a tuple of all these things, but we will see that there's reasons why you should do it. I will stop alluding to that and actually talk about it in a second. Okay, so I talked about pretty much all the things I wanted to talk about. It's right here. It's like next to this. It's actually LaTeX? Good lord. Okay, cool. All right. So yes, so cadd is curried, and this is how we'd use it. All right, I'm pretty sure this is like all I wanted to talk about. Yes, I got it right. Okay, early quiz. Take this one. Okay, sounds like some people might still be taking it. I'm gonna go ahead and get started with this next part because we got a lot of stuff to talk about. We got a whole zoo of HOF functions. All right, we're gonna take a ride on the wild side. Worth noting that I was looking while you were taking that quiz for the pieces of Haguruma chalk remaining, and there are nothing but like really small pieces left. So this is what I'm working with. I feel like I'm collecting infinity stones here, but all right. We're going to talk about the HOF Zoo, which are several higher order functions that come into play. We talked about how currying lets us return functions. We're going to have functions that are both curried and also higher order, and that will rather they take in functions. Okay? So for instance, oh, I know what I should have done during the break. I should have written this. Okay, well, whatever. Suppose I want a function that increments all of the numbers in a list, okay? And then not to keep you in suspense, I'm currently defining that function for you, right? So if I had x cons x's, I would just equate that to x plus 1 cons onto increment all of x's, right? This is like one function I could write, and this is like a fairly reasonably common pattern, right? And then suppose I had like a, suppose I had a function flip. Not flip1, it's just flip. And it just flips all the booleans in a list, okay? And I wanted to write that. Oh, okay, let me write it out. Actually, in some sense, it's educational for you to watch me write this, because my point I'm trying to make here is that this sucks to do, okay? Not x cons onto flip of x's. Reasonable, like this is of type bool list to bool, this is of type int list to int list, right? This one increments, this one negates. But it sucks to write, because if you squint your eyes, you go really far, you take off your glasses, like you look at it, like it looks pretty much the same, right? Like I'm kind of like doing the same thing, doing something to the element, and then I cons it onto the recursive column, the rest of the list, and then in the base case I return nil. So like these feel in intention the same. This is going to lead us to an idea of a higher order function called map. And map encompasses every possible function that lets us kind of do this. I realized I had some more motivation on the next slide, so I'm going to really fast context switch. Abstraction is the name of the game in computer science, really, if you think about it. For instance, we don't think about bits and bytes because we want to think about expressions and programs. We wanted to think about things like for loops and while loops rather than gotos, because this is better lets us communicate about what we do. The point I'm trying to make here is that higher order functions let us abstract over what this code is. We can write code that in turn kind of writes code for us, if that makes sense. Okay, and we're going to see examples of this soon. But that's kind of the real strength here of higher order functions, is how much we can encompass that idea, how we can capture common design patterns. So, all right, let's go ahead and do it. Here's what we're going to do. We're going to write map. And I'm going to give you the specification of map right here. Map takes in a function. The function is type alpha to beta. It means it takes in something and returns something possibly of a different type. I don't really care about what types particularly. We use polymorphism here because we don't want to constrain it. And then it takes in a type, a list of that first type, okay? And it returns to us a list of type beta list, which is whatever that output should be. So basically, in intention, map should evaluate to applying the function f that was enclosed to every element of the list. Okay, and you should convince yourself that this is going to be the design that lets us capture the idea of increment all or flip, so on and so forth. Okay, so let's try to write it, shall we? All right. So first thing we're going to do, and I remember I said something about how like I can throw off the shackles of type annotations, but I'm going to do it for possibly one last time because this is going to get confusing otherwise. So I take in an alpha list, and I return a beta list. So what happens if I try to map on the empty list? What do I get? The empty list, right? Let's do that. Recursive case, what do I do? So, all right, I have map f, and I have x cons x's. And what I really want to do is I want to apply the function f to the first element, and then apply it to the rest. Well, that sounds exactly like what I did over here, isn't it? It sounds like it should look very similar. So we'll do it. If I'm trying to apply f to x cons x's, that's the same as me applying f to x's. F to x, and then consing that onto the result of map f x's. And this is our higher order function, our first one. Well, after sort, that is. Okay? Map lets us do all of the things I just described. But now I don't have to go and write out this code because the code defines all of that code for me. All right? Let's see it in action. Let's give it a shot. Okay? If you believe me that this is the map function. All right, so let's try it out on map fn x goes to x plus 1 on like 1, 2, 3. All right, so I want to apply map to all these things. What do? I step, and the first thing that's going to happen is I'm going to case on it, right? I'm going to enter into one of these two cases here, and then I'm going to see that my argument is in fact not, like this x plus 1 right here. This is not of the form nil, so I enter the second case. That's applying the function fn x goes to x plus 1 to 1, and then consing it onto this, right? So I do that. I do 1 plus 1. I get 2. Then I recurse on x's, where x's is 2, 3. And then now I'm going to enter into the nil, not the nil case again, because 2, 3 is not nil. So I do that again. Actually, I can make this a little larger probably. So I apply. I do I apply the increment function to 2, I get 3, and I recurse again, but now I'm on 3. I apply the function to 3, I get 4, and I cons it on 2. Now I'm on x's is nil, so I enter into the nil case. And then finally, I collapse all the conses, and I'm done. Yeah. It was on the slide, I think. I didn't write it out, but this. Oh yeah, so this is a good observation, which is that the parens are important here, all right? If I write this type, alpha arrow beta to alpha list to beta list, okay? This is a function which the first thing it takes in is of type alpha to beta. It's a function of type alpha to beta. That is different than this. Why? Can someone describe why? Well, functions are values, so this is also a value. But it's taking in some, basically, the point is that it's taking in it's going to return a function, and this function is not the same as this function. So I guess the way I would describe it is, this is the first thing, the first arg, and this is the return. This is, in this one, this is the first argument, the type of the first arguments, any type, alpha. And then the return is something of this type. So if you want to think of like the curried arguments as like a number of functions, this one has 2 arguments, right? Distributed over curried functions, or over currying, and this one has 3. Okay? Does that make sense to everyone? Yeah. Yes, there are implicitly parentheses here because of right associativity of the type arrows. That's correct. I'm omitting them slightly. But you could be a little more explicit and write this out, and this would be fine to do as well. We typically don't, how do I say this? We typically don't write these parentheses because the usual mode of use of this function is we give these arguments, this one and then this one, simultaneously. But there are use cases for why you might want to return a function as your primary use case, and we'll see that in like 20 minutes. But that's a good observation. All right, everyone good on this? Okay. But that's how map works. And so now, what can I do? Instead of defining increment all and flip like this, here's what I can write. Let's do this. Fun, increment all, L. So if I want to increment a list L, now instead of doing that nonsense where I define it explicitly, I'm going to not make this recursive. Here's what I'm going to say. Map fn x goes to x plus 1 on L. And if I wanted to define flip, I believe that this is actually not exactly the example I had. Yeah, I had 2 string all, but I don't actually care. If I wanted to define flip, I would say map fn x goes to not of x onto L. Do people see why this should be increment all and flip? I'm mapping, which means I'm applying this function which flips everything, but I'm giving it as a lambda expression because I didn't want to give it a name. Yeah, you had a question? Okay. But I'm giving it this lambda expression because I didn't want to give this lambda or this function a name. I could have, of course, but I didn't want to. Okay. So this is how we can write increment all and flip, and we don't have to define it at all. Because why? Because it'd be code duplication. It'd be ugly. And then 2, every single time you write code, there's an n/m% chance that you write a bug. All right. I don't care if it's increment all. I don't care if it's flip. Like if you write enough of these, you'll start to write them wrong. Okay. I've done this. So it's a kind of a profound thing. Like by writing less code, we're by definition writing more correct code. Okay. That's like why you should think that code reuse really matters, other than it inconveniencing your life and your loved ones. Okay. So both of those things can be true. All right. Everyone good on yeah. Oh, these things. Yeah. Oh, that's a good idea. Okay. So let's do this one, right? Okay. So map has type. Well, I already wrote it, but I'm gonna write it again down here. This is true, right? It's of type alpha to beta to alpha list to beta list. Well, first, let's try to type check this, right? What is the type of this lambda expression? Int to int, right? So I'm passing in something of type int to int here. Right? Now, by analogy, I know this is going to get a little hard to see, sorry. But by analogy, alpha takes the place of int, and beta takes the place of int. Remember how we were doing type checking in the presence of polymorphism? That means that now I have alpha, where alpha is int. And I have beta, where beta now has a constraint that beta is equal to int. And if that's true, well, can't I just go and replace alpha and beta with whatever they are everywhere else? So I get parens int list to int list. And if you believe me, this whole thing is the type of this instance of map. This whole thing, and then so I take in the int to int, and I take in this function of type int list. And then SML will type check this whole thing to be of type int list to int list. Okay? Does that make sense? But this is kind of what's happening behind the scenes when SML type checks these things. That's a good question. Like, we're instantiating these polymorphic type variables based on clues given to us by what is passed in to the polymorphic function at the use site. Okay? All right. Okay, cool. But that's that. So we can write increment all and flip. Okay, any further questions on that before I move on? Cool. We have plenty of time, so. All right. Yes, and then I'll also say something about this increment all is extensionally equivalent to the previous increment all, and we'll give that a more detailed treatment in the third half. And by half, I mean third. Cool. But I claim there's something not great about this. All right. And it has to do with this thing back there. I don't know what I'm doing. This thing back there called partial application. Okay? I claim that I shouldn't really want to do this. Okay, let's see why. So I'm going to have to reuse some board space here. Increment all and map. The thing about map is that map returns to us a function. So why should I have to write out this declaration of increment all where I take in the L explicitly and I give it to this? Why couldn't I write something like this? And sorry, I'm going to keep going. I'm going to cover that up. But here's what I'm going to write. Does this make sense? Does this type check? Can I give not all of the arguments to map at once? The answer is yes, I can do this. Okay? Because let's compare and contrast them again, okay? So I've got increment all. I can either define it via saying increment all is equal to map given the incrementing lambda, or I can say fun increment all, taking in this L, is equal to map increment L, right? Well, let's see it in use, okay? Let's even, actually, I'm going to do it down here. It's more convenient. Suppose I wanted to use this second increment all. Let's call it increment all prime. I'm going to adjust the definition in a second. Let's call this one increment all prime. What would happen if I said increment all prime given 1, 2? Well, let's unpack the definition. So this would step 2 map. I should have picked a lambda. I wouldn't have to write out explicitly every time, and then given 1, 2, right? So this is what increment all given 1, 2 is. But let's use this one. What about that one? If I did just increment all, like without the prime, and I place it next to 1, 2, what would I have? Well, let's unpack the definition of increment all. It's equal to this thing, right? So this is extensionally equivalent to whatever that is, which is map fn x goes to x plus 1 next to 1, 2. And by Jove, aren't these the same thing? So if I put it next to its argument, no matter what, I've got something that where both of these things are equivalent to, at the end of the day, map given the incrementing lambda, and then the list I inputted. Okay? Even though the presentations were different, even though I didn't explicitly name this L when I did the above definition. Does that make sense to everyone? Does everyone see why these are exactly the same, pretty much? Yeah. Yeah, so I'm using this reduces to here because this is the literal definition of increment all prime, is that given an argument here, it will reduce to map of blah of this. I use extensional equivalence here because I wouldn't actually say that this reduces, I would not say this is a true statement. And this is kind of subtle. It's because when I bind increment all, this is an expression. So this goes to a value, right? It doesn't go to, this thing is not a value. So I can't say that this goes to that because that would be kind of like going backwards in time and saying that 2 steps to 1 plus 1. Basically, the thing I would rather say is that map of this thing here, okay, goes to like some function f, right? Some most reduced function, and then we produce an environment where f is bound to increment all. But in this context, I wouldn't say that. I think it would be proper to say that this actually reduces to f of 1, 2. That same f that I defined up there. But it would not be proper to say that it steps here. Do you see why that is? Because this steps to this. Or sorry, this steps to this f right here. But the f doesn't go the other way. This is more simple than map given this lambda. Basically what I'm saying is that map given that lambda is not the most simplified form it can be. So it wouldn't step to that, because that would be moving backwards in terms of simplification. Does that make sense? It's not like super important to know, but this is kind of like one of those really advanced things you should have an intuition for if you really hardcore like understand what SML evaluation is doing. How do people feel about that? Thumbs up, thumbs down. Okay. It's not super important. We're going to move on, but I'm free to talk about it after the class if people would like to. Okay. This is mostly a notation thing. Okay. All right. But let's move on. So the idea behind this thing I was describing up here is something called partial application. We're using map, but we're using it partially applied. I haven't given it all of its arguments, because if I don't give it the final list, I still get a value of type int to int. So the value in partial application is that now I can write stuff like that, where instead of explicitly defining increment all and toString all, I just use map given a single argument. And the next one is implicitly being waited for, okay? And we'll see a little bit more about that later. But this is the strength of partial application, is that it simplifies our code that we can write. Are people good on this? Any questions? Yeah. Yeah, map already takes in another argument. Like if we look again, I'm going to keep doing this. If we look again at like this place where I use increment all, this is just essentially equivalent to this, right? Because by definition, this is map given the increment. The place where the list comes into being is when I place it literally next to it. And then by definition, yeah, map expects another argument. I guess that's a fair way of saying it. Yeah, cool. Yeah, any further questions on this? Maybe I don't have enough time. I don't know. It's fine, we'll go with it. Okay. Okay, this is just the justification I just gave you. So this is something called ADA expansion. This is not super important, but you can say it to sound cool to your friends at parties. But the idea is that if I have f of type t1 to t2, f is always extensionally equivalent to fnx goes to fx. Does everyone see why this is? Like, this equivalence always holds. Because it's no different from me saying f, which is a function. F is a function. It just is. Versus saying a lambda expression, a function that takes in an argument and gives it to f. If I were to use this lambda, I would give it to f anyways. The most easy way you can see why this is true is if you do this. Suppose we're giving it a value v, and this literally reduces to fv. So for all values v, this one reduces to that. So therefore, this must be extensionally equivalent to that. Does everyone buy what I'm saying? If not, please speak up. Okay. That's called ADA expansion. It's not super important, but the idea is that you can simplify your code by removing places where you see this. Okay, that's kind of why I said earlier this is gross, because I noticed that this was the ADA expanded version of that. By that I mean, here I have. Let me use colors. Yeah, I have L here, and I have L here. And what did I do when I defined increment all above? I cut out the middleman. I removed the L. I took the L, you could say. All right, everyone cool with that? All right, great. We do have other stuff to cover. Cool. But the idea here is just that map is a hierarchy of functions. Map defines every function that involves transforming the data in a list. Hey, there are so many more applications than just the two I showed you here, increment all and flip and whatever, okay? But that's kind of like one of the beautiful things about higher order functions. Okay. And yeah, so another thing I showed you, this kind of came up on your quiz, but when we defined sort earlier, we had it be tupled. We had sort that took in the comparison function and also the list, both at the same time. But if I wanted to, I could curry the function. Does everyone get what I mean when I say that sort curried is the curried version of sort, in the sense that instead of taking in a tuple, I'll write it down. Instead of taking in a tuple, which is alpha star alpha to order, and then star alpha list to alpha list, the type of sort curried is where I just change this to an arrow. Yeah. Yeah. I would not say that that was true if f were not a value. Sorry, I implicitly was quantifying over values. I would not say this is true if f were not a value.
Okay.
Yeah, yeah. That's actually a very good observation. That in fact, I'm going to claim to you if f looped forever, this would not hold because this would loop forever. This would not. Okay. You don't have to see why that is right now. We'll cover this in about 5 weeks. It's called laziness. But there's also something good to know now, I guess. But yeah, the things in lambdas are frozen. I'm not going to give this more treatment because I'm talking about this next lecture. But yeah, good observation. Really good observation, actually. All right, cool. So if I wanted to curry my sort function, here's what I would do. And then I could define all of these int sorts and string sorts and mod 12 sorts just by using sort curried in a partially applied way. That is to say, I give it just the sorting function. I don't give it the list. And each of these are themselves functions. Int sort is a function of int list to int list. String sort is a function of string list to string list. Does everyone see why I can do this? Because I've curried it so that I'm leaving the L unspecified, but it's still going to be taking it in. Okay? Does that make sense? Yeah. Maybe I didn't give, yeah. Actually, I totally lied. I don't have enough time. Okay. And this is really powerful because remember that big page I had where I said merge sort can be written so fast? It's still 20 lines. I don't want to write 20 lines for each of these sorting functions, okay? Now I can. All right. Cool. Let's go ahead and do it. Yes. And I just have some extra remarks here where like map has basically like the Platonic structure of transforming listed data. I get a little philosophical there. It's not really important. Cool. Another thing that is very common is that we usually want to like take in a list of things and we want to keep only the elements of the list that satisfy some condition. And that should sound like a higher order function to you when I say some condition, because we're going to be concretizing that by abstracting over it. Okay? This function is going to be called filter. Here's what it does. A function filter has type alpha to bool, takes in an alpha list, and returns an alpha list. Okay? And it just evaluates it cuts out all of the elements in the list that don't satisfy that predicate. Okay? I'm going to write it for you really fast. But if you understand map, you probably will understand how filter works. So filter given the empty list is just the empty list. But if I have p and x cons x's, where p is this function of type alpha to bool, I have two cases. Either px is true, in which case I'm going to, oh, sorry. This is not the right case. X cons filter px's, else filter px's. Does everyone see why this is true? So if my element I'm currently looking at satisfies the predicate, I keep it and I recurse. Otherwise, I don't keep it and I recurse. And sort of inductively, you're going to keep only the elements. Recursively, this will mean that filter will only ever keep elements that satisfy P. Is everyone good in this? This is like strictly easier, I think, than map, to be honest. Okay. Okay. If no questions, we will move on from this. And filter can be implemented like so. Who would have guessed? Well, with different indentation. That's fine. I woke up on the different side of the bed today. Okay. So here's the use case for a filter. Suppose I wanted to write stuff, and I'm not going to write all this out. I'm going to let you look at it. But here's what I'm going to do. I'm going to define an is-even function. It's just a lambda, takes in a number, and tells you if it's even. Then I have a keep evens function, which is filter is even. Let's actually work through it. What is the type of keep evens? Can someone tell me? What do people think? So I claim to you is even is of type int to bool. Okay? What about keep evens? Which is the application of filter. I realize I put away the type definition of filter, so maybe it'll help if I write it out up here. Alpha to bool to alpha list to alpha list. Okay? So the type of keep evens is going to be given this int to bool function, taking the place of that. It's going to be whatever's left, but with alpha replaced with int. So I've claimed to you that keep evens is of type int list to int list. Okay? Because I've partially applied it, even though its filter takes in 2 arguments, I've given it only 1. That's okay because of partial application. Then isn't it the case that keep evens given the list of 1, 2, 3, 4 should be of type int list? And in fact, this is true. Keep even, I'm showing you that this is what it evaluates to. Keep evens 1, 2, 3, 4 will evaluate to 1, 3. And if you step through all of the filter stuff, you can think about why. But one of the really cool things here is you don't need to think about how filter is implemented. Think about filter at the high level. What does filter do? It keeps stuff that satisfies this. So obviously, filter is even on 1, 2, 3, 4 should be 1, 3. I'm saying obviously, it might not be obvious to you, okay? But if you think about it at the high level, I claim you can see what this is, all right? And if I define keep odds, I claim to you that this lambda right here is also going to be of type int to bool. And therefore, keep odds, who would have guessed, is also going to be of type int list to int list, okay? So then if I use keep odds on 1, 2, 3, 4, I'm going to get 2, oh, whoops. Thank you. You know, it only takes me like 3 minutes of talking through this slide before I notice. Thank you for that. Yes, it's flipped. But if you think about it at the high level and you actually read the slide, keep evens on 1, 2, 3, 4 is going to be 2, 4. All right. And then keep odds is going to be 1, 3. Yes. Applying functions in pandas. I'm not familiar with pandas, but I would assume so. Yeah. Python has great functions. It's like an iter tools thing or something. Yeah. The 150 grading infrastructure used to use it. Yes, but that's how that works. Cool. Any other questions on this? Sorry for the typos. I don't actually like check when I'm making these. Yeah. Are there other languages that don't? C does not have a proper notion of curry functions. C, you can only pass around function pointers, which are strictly less useful than first-class functions. Not important, by the way, but C does not have such things because C does not have nice things. K and R really dropped the ball on that one. All right, so but this is the example. Everyone cool with this? Good question. Fun question. But I hate this. All right, I had to write fn x goes to not of is even of x. I had to write 2 parentheses here. I had to explicitly give a name to my variable I was taking in. I hate that. You'll find that, I think I say it here, some functional programmers would rather be hit by a bus than have to write out an explicit lambda expression. I'm not usually one of them, but in this case, we can do better, all right? And maybe you don't know that we can do better because we haven't seen that we can do better. Here's your other lesson of the day. You can do better. I believe in you. But we're going to try and do better, all right? So, for instance, by analogy, let me give you this, okay? I would rather write map fx's than map fn x goes to fx of x's. This is the eta expansion of f, right? Via what I told you earlier. But I claim to you this is strictly uglier than that. Does everyone see why? Like, I had to write more, okay? I claim to you that this is ugly for that same reason. But it's not clear on how I should write it. So let's figure out how to write it. And this is going to lead us into something that's going to satisfy the mathy people in the audience. Well, you're all mathy people. Because this is going to be called function composition. Something you learn about when you're like 6 is function composition, which is, straight. That's not true. I'm lying. I didn't learn about it when I was 6. Function composition, right? Where I can do g compose f, and then this on x should be equal to f of g of x, right? And this is like a nice notation I can write because this just makes my life easier when I'm doing math, right? I want to write less symbols, okay? But turns out we can do something similar in ML, okay? So we're going to write a function compose, and all we know about this is that g goes from some type to some type, okay? This is like in the math sense, right? G maps from T2 to T3, and then F maps from T1 to T2. Ah, shoot, did I? Sorry, my bad. I explicitly was thinking, okay, should I write F O G or should I write G O F? I'm gonna write F O G because then I can write F of G of X, or G of F because of that same reason, and then I flipped it when I went here. Sorry. Thank you for pointing. I'll give a high chew to everyone in the room for speaking up. I'm joking. I can't do that. And that means that this whole total composition should map from T1 to T2, right? T3, sorry. Does that make sense for everyone? Thank God, I finally said something right. But let's do it in SML. So what does it mean for any function T1 and T2, for any types T1 and T2, and any types T2 and T3 to do something? It means I've got polymorphism involved, right? Because that lets me take in anything. So here's, I believe, my spec of compose. Compose takes in a tuple of two things. One of them will be a function from beta to theta, and then one of them will be a function from alpha to beta, okay? And I'm going to return to you this, yeah. Run with it for a second. Oh, actually, I spoil it here. There's an infix operator O defined in SML that does that. Yeah. Compose can be, just replace compose with O. I was trying to hide it from you, but I actually spoiled it here. But yes, compose is pretty long, but let's define it. Let's actually pull away the wool, all right? So let's do it. So assuming that we have an infix operator O, here's how we define it. If I have G O F, remember that this is our infix operator defining syntax. I put the first argument here and the second argument here. This is going to be equivalent to fnx goes to g of fx. Okay, this is of type, right? I said it earlier, but I'm going to emphasize it here. Beta to theta to alpha to beta. 2, and I claim that actually here, to answer your question, this is where I might want explicit parentheses. Because my main use case for compose is I produce a value of type alpha to gamma, or theta. If I do this, and I usually give it this argument, that will be fine, like if I explicitly write out the x, but usually I'm not. Usually I'll just say, I've got GOF, and that's it. That's all I want. And maybe I bind this to like a value, okay? So I claim like it might be in intention better to put the parens here. Again, it doesn't matter because they're equivalent, okay? But this is the type signature of compose. Is everyone good with that? Okay, let's revisit our life decisions, which is here when I wrote fnx goes to not is even x. Can someone tell me what I can do here to make this less ugly? What do I do here? Yes. It happens to be convention in NJ that everything usually is like infix operators rather are tupled. It doesn't need to be the way. In Haskell it's not the way. In OCaml it's not that way. Ask Bob Harper up in 9115. Not 9115, but one of the 9 offices. He designed the language. He'll tell you why. But yeah, I don't know. Cool. But yes, what do we do here? Yeah. So let's try it. So you said, let me put it up here. You said not is even. So is even is of type into bool, right? And not, if you can see this, not is of type bool to bool. So will it type check if I give this as with this type as input here, where it's expecting a bool? No, not quite. Yes. Let's compose it. That's all we needed. Good one. Who would have guessed after defining compose, we're going to use the composition operator? But sorry. If I compose both of these two things, because doesn't this look exactly like f of g of or g of f of x? It's the same thing. I've got g o f, which is defined to be the same thing. Like if you look at these two things, they actually pattern match onto each other, right? So I can avoid all my troubles and an extra parens and a lambda expression by writing it writing it as such. Okay. So instead of doing what I was doing before, where I don't have it on the board anymore, but I would instead say that is odd is not oh even is even. Or if I didn't even want to give it a name, I would instead just use, I'm going to write here, filter not O is even 1, 2, 3, 4. And this whole thing type checks, and this whole thing is the same thing, so this should be not even, oh yeah, it's 1, 3. Okay? I'll write it out. Is everyone good with this? Yes. Oh, a definition composition. Oh, this thing, like around here. Here. Oh, shit. Like here.
Yeah.
Oh, I see what you're saying. Sorry, I'm used to that. This binds tighter. This tuple binds tighter. So by convention, it would probably be more clear to write it this way. But I'm used to the fact that function arrows, basically the way you should think about it is function arrows are like the weakest thing around. Like they always go last. So everything between function arrows is like its own thing. Okay. Yeah. But that's a good point. Cool. Okay, I got 15 minutes to talk about folding, so we're gonna do that. Okay. How many of you write Python? Raise your hands right now. Okay. TAs, can we take off some points from, no. All right, so a very common pattern in Python, I claim to you, is where you do something like this. All right. Actually, let's not call it X, let's call it ACK. All right, if you don't know Python and you don't read this, like it's fine, just read it as pseudocode. But a very common pattern is I say I got something ACK, I set it to some default value, and then for everything in a list, I like do something. Yes, I do something with X and then I assign it to ACK, right? Maybe also ACK is involved in there, okay? Okay, like you see what I'm doing? I'm kind of like doing something for everything in the list. For instance, summing everything in a list takes this form, right? Well, if you don't want to use like, the sum thing or whatever, then I would say like ACK plus X, right? Fair enough. I hate having to do this. I had to write out a for. That's too much for me. We don't even have for loops in, that's actually not true. That is true. We don't even have for loops in SML, all right? So this is like, as an analogy, it doesn't precisely work. But the point is, I don't want to have to do that if I've got other avenues open to me. So let's try to do that. So the idea here is that we're summarizing everything in a list. We're trying to do something for every item in a list and not necessarily produce a list as output, right? Because if I map, I always get a list as output. But if I sum everything in a list, I get an int. So let's write it. This thing is called folding, all right? So basically the idea is like if I write ML functions like sum, I sum for everything in the list, or I concat a list of strings, I'm going to use my concatenation operator with my base case of the empty string. Or if I'm trying to flatten a list, right, as you do on your homework, if I'm cheating and I'm allowing to use append, I would instead append where my base case is nil. Right? Does this make sense to everyone that this is like a thing that sometimes we do? Well, again, squint your eyes, go 50 steps back, and then look at it. Like these look the same. So let's try to fix that. This is something called folding, as I already did it in reverse order. But all right. Here's the point. I'm going to define a function that's got a really complex type. Okay, and we're going to work through it. This is the type: alpha star beta to beta, to beta, right? Yes, to alpha list, to beta. Let's work through it, all right? It's 4 parts. This, and this, okay? The first thing I've got is what I call my transforming function. It's what I do for every element in the list. The way you should think about it is beta is the type of accumulator. I'm essentially automating the process of what we did with t-length and t-rev and whatever. I'm having an accumulator beta, okay? So beta is all of these guys. And then alpha is the type of elements that I'm using to transform my data. So if I'm folding with this, I'm taking in a function that uses an element from the list, it uses an accumulator, and it produces a new accumulator, okay? I call this the transformation function, all right? It's the function I'm calling for every element in the list. This is my, what I call initial accumulator. It's my initial value. The same way that when I was writing those functions earlier, like sum and flatten, I had base cases of like 0 or nil, right? That's my initial accumulator. And this is my list to be folded. Okay? and I get out my final accumulator. In terms of purely the type, do you see what this is doing? Do you see why this should be a thing that works? Okay? I'm saying, give me an accumulator, do something to it for every element in this list, right? And produce a new accumulator each time, and eventually we'll get out the final accumulator once I run out of elements, okay? The same way that if I had this is my initial accumulator. For every element in the list, I'm going to call f x and ac and reassign ac, so I produce a new accumulator. And eventually, once I'm done, I'm going to, I guess the corresponding analogy is I return ac, okay? Spiritually, do you see what I'm saying here? We're going to look at some precise examples, but this is the type signature for fold, and we're going to go and implement it, okay? The idea is that we're just keeping an accumulator with us, and we change it for every element in the list, all right? I'll leave this up. Cool. This is our type signature. Fold L it has that exact type I just described to you, but fold L is going to fold from the left. What I mean by that is if I have a list of x1, xn, if I fold L, and by convention, this is usually called F, and then Z, my initial accumulator. This is going to evaluate to this. F given xn, iterate that process, and in the very middle, I'm going to have F given x2 of F given x1 of Z. So what I mean by that is I'm going to take the first thing off. I'm going to combine it with my initial accumulator Z. I take that result, the result of doing the first x element, and I combine that with x2 using F. And then I keep doing that, keep carrying along that result until eventually, finally, I combine it with xn. The idea is I just have an accumulator, and I'm going to update it using F with every element of the list. Okay? I'm trying to speak in very broad, like high-level terms so that you get the algorithm, like what it's doing into your head, the specification. Is everyone good on this? And it's called fold L because what order are we doing it in? The innermost one is x sub 1. So the first thing that we fold is x sub 1. We do it from the left. We take the accumulator and we put in everything in it, going from left to right. Okay? All right. I guess I'll use, I don't actually care. Let's implement it. So here's what I'm going to do. I'm going to write on this board. And remember, this is the type specification up there. Fold L, F, Z, nil. If I have no elements left, and I want to combine my accumulator with all of the elements in the list, I just return my accumulator, right? I have nothing left to combine it with, okay? If I'm trying to fold L, and I have F, I have Z, and I have x cons x's, right? That's my next case. What am I going to do? Well, I told you earlier, the first thing I want to do is I want to take that x1 and combine it with Z, and then keep recursively going forward and pay that back. So I claim to you what I'm going to do is this. Fold L, F, the same F. What I'm going to do, F of x comma Z, x's. Okay? This is what I'm going to do. Okay, in retrospect, I definitely misjudged how much time I had originally. But the thing you have to realize is the first thing I do is I take the first thing off and I combine it with my accumulator. That's going to correspond to folding left because I want to go left to right. Okay? And then I'm going to recursively do that for the rest of the list. I take my accumulator and I change it once, and I keep changing it for everything else in the list. Okay? And kind of like the order we can quibble about later, but this is what the algorithm is doing. Okay? The existence of fold L implies the existence of fold R. So let's talk about fold R, which has this is an aside of how we'd use it. But basically, if I wanted to use fold L, if I wanted to define the function that sums a list, instead of writing the sum, I would write fun sum L is just folding with the plus function and given 0. Op is how I turn the infix operator plus into like a real function. Okay, that's just syntax. But if I fold with plus in a base case of 0, I'm going to sum everything up in the list. Do you believe me in terms of like analogy to how this looked up here when I had ac is equal to x plus ac? Yeah. Yes, you can. Because it's just a value. Op plus is just a value. Yeah. But what I'm saying is that fold L op plus 0 is essentially this code. I mean, this Python code. but it is exactly this ML code. Okay, well, the sum function I defined earlier, okay? How you would normally define the sum function. Do people believe me on that? Does that make sense? Okay. Yes. The 0 is the default value. If I told you sum up everything in the list, you probably intuitively would be like, okay, yeah, I'm going to start from 0 and then change it for every element. But you have to explicitly say that. It doesn't know where to start. One of the strengths of actually doing this is that we could sum up everything, but sum it to a base of like 5 or 10 or whatever. That's customizable. But it happens to be that 0 is our right choice for this problem. But yeah, good question. Yeah. Yeah, in the base case, you already returned z. I claim to you, actually, you literally cannot make the function type check with the type signature up here unless you return z. Because I have this thing, which is not a beta. I have this thing, which is not a beta. How do I get a beta? I have to give it the initial accumulator. But also in intention, it's because, do you remember how we return the accumulator in like t-length and t-rev at the base case? Same principle. I can only return the accumulator once I'm done. This is just a generalization of that tail recursive stuff I was telling you about. Wow, there was a point to all of that? No way. All right. Oh, here's a trace actually, so I can show it to you. This is important. If I want to use sum, by definition, that is full del given the add function, given 0, given 1, 2, 3. The first thing I do, based on my definition of full del over here, the first thing I do is I go to full del, but I'm going to use that function on what? The first element and the accumulator. So I add 1 to 0, right? Because I take the 1 off and I combine it. And then I get 1. And then the next thing I do is I take off the 2, I add it to my accumulator. That's 3, and I move on. And then what I do, I take off the first element, 3, I add it to my accumulator, 6, and I go on. Now I'm at nil, so I return z, so I return 6. Does everyone see why sum returns the sum of the list? This is just to show you like what it's doing. Like really all I'm doing is I fix this accumulator, and I keep taking things off the front of the list and combining it with it. I take another thing off, and I put it into the accumulator using that same function I defined up there, okay? That's your intuition for why this should work. I'm gonna really quickly do this. Okay, fold R is gonna be the same thing, but instead of being that I take the first thing off, the first thing I do is I take the last thing. So, Nope, linear work still. But the idea is like if I have x1 through xn, xn, I'm going to, first thing I do is I take off from here and I give xn to z. And then the next thing I do is I take off the next element and I do f of xn minus 1 to that, ... You see how this iterated is pretty much the opposite of what we just had, yeah. Yes, that is a trade-off, but it doesn't need to be. Let's implement it first, and I have some remarks on that. So let's define it, where fold R still has that same type, okay? But it does it in just a different order. F, Z, nil. What do I do when I don't have any elements left? I return the accumulator, so I'm going to return Z. Actually, I don't know why we call it Z. It should have been called ACK. Whoops. And if I have x cons x's, here's what I'm going to do. I have the first element of the list right here. But I want to do that last, right? The last thing I want to combine is x. So here's what I'm going to do. I'm going to combine x with something. But I'm going to do the rest of it first. I'm going to do the rest, and then I combine with x. So what do? In some respects, this is actually easier than fold L, I think. But I'm actually, in a very deep sense, it's easier than fold R. I combine the rest of the list, I sum the rest of the list, and then I sum with the first element, right? The difference between these two implementations is first element, or, do I combine with the first element first or the first element last? This is first element last, FEL, let's say. Fold L, because I do it here, and eager evaluation means this goes to a value first, is first element first, okay? Is everyone good with this? I have pretty much no time left, so I'm going to, yes. Okay. I claim to you we can implement the sum, concat, and flatten via how we did it here. There's something else I wanted to tell you, which is that for most applications, fold R is the most natural fold. And I'm not going to be able to show this to you exactly, even though I told the TAs I would. But here's my claim, all right? So op cons. So if I fold L using cons and a base case of nil on some list L, I claim to you this is the same thing as reversing the list. Okay? I do not have time to work out with you why this is. I probably am going to pick up this lecture from where I did it, but I highly recommend looking through these slides and figuring out what the hell these things do. I have plenty of examples. Okay? Thanks. Thank you so much. Blue team won. Yeah.